Java interfaces and packages. Welcome everyone. Today we'll explore one of the most essential and powerful features of the Java programming language, interfaces and packages. Those two concepts play a crucial role in writing clean, modular and maintainable code in Java, especially as your projects grow larger and more complex. Let's start by understanding what interfaces are. In Java, an interface is a blueprint for a class. It defines a set of method signatures that any implementing class must provide. What makes interfaces so powerful is that they allow us to achieve abstraction. We can define what should be done without worrying about how it's done. Interfaces are also Java way of supporting multiple inheritance since a class can implement multiple interfaces. On the other side, we have packages. Packages act like folders or namespace that help us class, organize classes and interfaces into a logical structure. This makes your code base easier to navigate. Imagine having hundreds of classes in one file. Packages solve that problem beautifully. Some of the key benefits we will discover today include abstraction, modularity, code reuse, and namespace management. Agenda. Before we get deep into the topics, let's take a moment to look at today's agenda. This will help you us understand the flow and what to expect from this session. We will start with the very basic by answering a fundamental question. What is an interface in Java? We will explain the definition, the purpose, and where interfaces fit into the object oriented model. Whether you are a new to Java, this session will start the stage for the rest of the presentation. Next, we will explore the syntax and rules of interfaces. There are several unique characteristics of interfaces, like how all methods are implicitly public and abstract, and how variables are automatically public, static, and final. Then we will into an important comparison interfaces and abstract class. This is a common area of confusion for beginners. We will break down the differences and help you understand when to use each. After that, we will explore how to implement and extend interfaces, including examples of multiple inheritance through interfaces, something Java does not allow with the classes. We also cover real world use cases showing interfaces in action in real Java applications. We will discuss popular interfaces like runnable, comparable, and serializable. Following that, we will shift your focus to Java packages. We will define what they are, why they matter, and how to create and use them effectively in your programs. Lastly, we will wrap up the best practices and common mistakes to avoid. This includes tips for clean interface design, package naming conventions, and more. So, get ready to deepen your understanding of Java. Let's move forward with the first main topic, what is an interface in Java? Now let's see our first main topic. What is an interface in Java? Understanding this concept is essential because interfaces form the backbone of Java approach to abstraction and polymorphism. In simple terms, an interface in Java is like a contract. It contains a list of method declarations or method signatures but no method bodies. That means interfaces don't provide any implementation for the methods they declare. Classes that use or implement an interfaces must provide the implementation themselves. This way, any class that implements it agrees to define all its methods. For example, imagine we define an interface called vehicle with a method start engine. Different classes like car, bike, or truck can implement these interfaces and provide their own unique version of the start engine method. The interface just defines what should be done and the classes define how it's done. Why is this useful? Well, interfaces help in achieving abstraction, a key object oriented principle that allows us to hide the complex implementation details and only expose the necessary behavior. They also allow us to create loosely coupled systems where different components communicate via interfaces rather than being tightly bound to specific implementation. Another major benefit is that Java supports multiple inheritance of types through interfaces. While a class can only extend one superclass, it can implement multiple interfaces, allowing more flexibility in design. In practice, interfaces are used everywhere in Java. For defining custom behaviors to implementing common design patterns, you will often encounter built in interfaces like comparable, runnable, and many. Let's now move on to understanding the syntax and rules of interfaces in Java. In this section, we will the syntax and rules interfaces in Java. While the concept of interfaces is relatively simple, Java enforces specific rules that you need to understand and follow when defining and using interfaces. Let's begin with the basic syntax. Here, simple example. In this example, we have defined an interface called animal with one method make sound. Notice that there is no method body. We are only specifying what the method is, not how to works. Any class that implements this interface must define the actual behavior of make sound. Now let's go over the rules. First one, all methods in an interface are implicitly public and abstract even if you don't write those modifiers. So writing white make sound is the same as writing public abstract white make sound. Second one, variables defined in an interface are implicitly public, static, and final. This means that you can declare constants in an interface but not instance variables. Third one, interfaces cannot have constructors since they are not classes and cannot be instantiated directly. There's no need for a constructor. Fourth one, starting from Java 8, interfaces can have default and static methods with implementation, but only under specific use cases. This is to allow backward compatibility and convenience. Fifth one, a class implements an interface using the implements keyword, not extends. Those rules ensure that the interface remain clean and focus on defining behavior, not state. Next, we will look at why interface are so important and the advantages they bring to Java development. Why use interfaces? So now that we have seen what an interface and how it's structured, the next important question is why should we use interfaces in the first place? The primary reason in abstraction, interfaces allow us to define a set of behaviors without specifying how those behaviors are implemented. This helps developers design systems that are flexible and loosely coupled. Think of it like defining a role in a team. You are not specifying who should fill the role and just what the role requires. For example, consider an interface payment processor with a method process payment. Different classes like a credit card processor or bank transfer processor can implement this interface in their own way. The application using those classes does not care how the payment is proceeded. Is just know that process payment will be available and will do the job. This approach promotes separation of concern, which is a critical software engineering principle. Another reason is multiple inheritance of type. In Java, you cannot extend more than one class due to the risk of ambiguity known as the diamond problem. However, with interfaces, a class can implement multiple interfaces, enabling multiple inheritance. This means a single class can inherit capabilities from several interfaces, make your designs more flexible and adaptable. Interfaces also standardized behavior. When multiple unrelated classes implement the same interface, they are to provide the same methods, making your code more predictable and easier to manage, especially in larger teams or open source projects. In short, Interfaces are essentially for building scalable, maintainable, and flexible applications. They are key tools for enforcing contact based programming and designing robust applications. Let's now compare interfaces with another important object oriented programming concept, abstract classes. Now let's talk about a common question that Java beginners often ask: what is the difference between an interface and an abstract class? This comparison is essential because both are used to achieve abstraction, but they serve different purposes and have different rules. Let's begin by understanding what they have in common. Both interfaces and abstract classes are incomplete types. You cannot create objects directly from them, and they are designed to be extended or implemented by other classes. They both allow you to define methods that a subclass or implementing class must override. But beyond that similarity, the two are fundamentally different. Take a look at the comparison table from this side. Inheritance. An interface supports multiple inheritance. A class can implement multiple interfaces. A class can extend only one abstract class. Method types. Interfaces can only have abstract methods until Java 8 when default and static methods were introduced. Abstract classes, on the other hand, can have a mix of abstract fields. In interfaces, all fields are implicitly public, static, and final, which means they are constraints. Abstract classes can have instance variables and they can be private, protected, or public. Constructors. Abstract classes can have constructors which can be called from subclasses. Interfaces cannot have constructors because they cannot be instantiated. So, when should you use one over the other? Use interfaces when you want to define a contract for behavior, especially when multiple classes, possibly unrelated, will implement that behavior. Use an abstract class when you have shared code or state that that multiple related classes should inherit. Understanding the differences helps you make more intentionally and clean design decisions in your Java projects. Next, let's explore how we can implement and extend interfaces in real code. Implementing multiple interfaces. One of the most powerful features of interfaces in Java is that they allow a class to implement multiple interfaces. This is Java way of providing multiple inheritance not of implementation but of type. This flexibility makes interfaces a key tool in designing extensible and modular applications. Let's break it down with the simple example on the slide. We have two interfaces, flyable and swimmable. Each of those interfaces declares a single method, fly and swim. Then we have a class duck that implements both interfaces. This is a simple but powerful concept. Duck is now both flyable and swimmable and can be treated as either in different contexts. This supports a flexible polymorphic design. For example, you could write a method that only take a flyable object and pass it a duck, eagle, or even an aeroplane, as long as they all implemented flyable. In class inheritance, you can only extend one class, but with interfaces, you can implement as many as you need. This helps is creating classes that have multiple behaviors without worrying about inheritance conflicts. This approach is common in frameworks, libraries, and large applications where separations of concerns is critical. It's also a good practice to design small, focused interfaces that can be combined as needed. Extending interfaces. In the previous slide, we see how a class can implement multiple interfaces. But did you know that interfaces themselves can extend other interfaces? This is an important feature in Java that supports a modular and a hierarchical structure of behaviors. Let's understand how this works with the example shown. In this example, interface B extends interface A. This means that B inherits all the abstract methods of A and can define its own additional methods. Any class that implements B must now implement both method A and method B because B includes everything from A. This approach is very useful when you want to refine or expand functionality in a controlled manner. For instance, suppose you are building a system where all devices must have a connect method. Another great feature is that can interfaces extend multiple interfaces. That's right. Just like a class can implement multiple interfaces, an interface can also combine multiple behaviors by extending multiple interfaces. This allows you to compose interfaces in a highly modular and reusable way. By using interface extension, you can design systems where new types can evolve naturally from existing ones, supporting scalability and maintainability. Now let's see more complete example of this concept in action with a real-world interface inheritance example. Interface inheritance example. To better understand the concept of interface inheritance, let's walk through a real world example that combines multiple interfaces into a single interface and then shows how a class can implement it. In this example, we define two separate interfaces, printable and scannable. Each one represents a different behaviors. Now we create another interface called multifunction that extends both printable and scannable. Interface multifunction extends printable scannable. This means that multifunction is a composite interface that represents both capabilities. Any class that implements multifunction must know implement the print and scan methods. Here show a class called printer would implement it. This is a classic example of interface inheritance and multiple behavior composition. Rather than putting all methods into a single interface from the beginning, we create small focused interfaces and then combine them as needed. This design pattern is often called the interface segregation principle, one of the solid principles in object oriented design. It allows greater flexibility and reusability. For example, if we later want a device that only prints but does not scan, we can implement just printable. This pattern is widely used in modern software development and frameworks. Interfaces like list, queue, and set in Java collections follow similar principles, modular, extendable, and focused. Now that we understand traditional interfaces, let's look at a special kind of interface introduced in Java 8, functional interface. Functional interfaces in Java 8 Plus. Java 8 brought a lot of existing features of the language, one of the most powerful being the introduction of functional interfaces, which are at the heart of Java, support for lambda expressions and functional programming. So, what exactly is a functional interface? A functional interface is an interface that contains exactly one abstract method. This makes it ideal for representing a single operation like performing a task, comparing two values, or transforming data. Those interfaces are meant to be used with lambda expressions, which allow us to write shorter and more readable code. Here is a simple example. The functional interface annotation is not required but is highly recommended. It tells the compiler that this interface should have only one abstract method. If you if you try to add another abstract method, that compile will generate an error. This ensures that the interface stays to its purpose. Now with this interface in place, we can use a lambda expression like this. This is where more than creating an entire class with a method implementation just to execute a simple action. It allows supports a functional programming style, allowing Java developers to write code that is more declarative and easier to parallelize. Java already provides many built-in functional interfaces in the java.util.function package, such as predicted, function, supplier, and consumer. Functional interfaces unlock a new paradigm of programming in Java, one that emphasizes cleaner, more readable, and more maintainable code. Now let's explore some real-world use cases of interfaces that you will encounter frequently as Java developer. Real-world interfaces use cases. So far we have explored how interfaces are defined, used and extended. But theory only takes us so far. Let's you now look at some real world use cases of interfaces in Java. Those examples will help you understand how interfaces are used in practical everyday development. One of the most commonly used interfaces is runnable, found in the java.language package. This interface represents a task that can be run on a separate thread. It contains just one method run and is therefore also a functional interface. Here how it's typically used. By implementing runnable, we can define tasks that can run in parallel, essential for multi-threading and concurrency in modern applications. Next, we have comparable, which is used for sorting objects. This interface is found in the java.language package and contains a single method called compare_to. For example, if you have a list of student objects and you want to sort them by grade, another critical interface is serializable from java.io. This interface is used to indicate that objects of a class can be converted into a byte stream and saved to a file or sent over a network. It's marker interface, meaning it has no methods. All those interfaces demonstrate how Java uses them to represent behavior contracts that can be flexibility implemented across many classes. Now let's transition from interfaces to the next major topic in your session. Java packages. What is package in Java? Now that we have covered interfaces, let's shift your focus to the second major topic of today's session, packages in Java. A package in Java is essentially a namespace used to group related classes and interfaces together. Think of it like a folder system on your computer. Instead of dumping all your files into one directory, you organize them into folder, and that's exactly what packages do for your Java classes. For example, Java has packages like java.util, java.io, and java.language. Each package contains a set of related classes and interfaces. Java.util includes utility classes like ArrayList, HashMap, and collections. Java.io deals with input-output functionality, while java.language contains core classes like string, math, and system. Packages serve multiple purposes. Organization. They help keep your code base clean, manageable by grouping related functionality together. Avoiding name conflicts. You can have two classes with the same name for as long as they are in different packages. For example, you can have com.example.service.user and com.example.model.user. Access control. Packages play a role in Java access control system. Your code base clean, manageable by grouping related functionality together. Avoiding name conflicts. You can have two classes with the same name for as long as they are in different packages. For example, you can have com.example.service.user and com.example.model.user. Access control. Packages play a role in Java access control system. For example, members with default access are only accessible within the same package. Reusability and maintenance. Code organized into packages is easier to reuse and maintain. Larger applications often have hundreds or even thousands of classes and packages make complexity manageable. To define a package in Java, you simply use the package keyword at the top of your .java file. Package com.example_utils. From this point onward, this class becomes part of the com.example.utils packages. Next, we will explore the different types of packages available in Java, built-in and user-defined. Package private access by default. This means the class or member is only accessible within the same package, not outside. Fourth one, private. This is the most restrictive. Private members are only accessible within the same class. You cannot access them from any other class even if it is in the same package. Understanding how those access levels work ensures proper encapsulation, modular design, and safe code exposure. You avoid accidental usage of internal classes and maintain a clean separation between your application and internal logic. Access modifiers and packages. Understanding how access modifiers interact with the packages is crucial when structuring your Java applications. Java provides four main access levels: a public, protected, default or no modifier, and private. Those control the visibility and accessibility of classes, methods, and variables and are deeply tied to how packages work. Let's break them down one by one in the context of packages. First one, public. When a class, method, or variable is marked as public, it is accessible from anywhere, even from outside its package. If you want a class to be used across your application or by third party users, make it public. Second one, protected. This modifier is more usable. It allows access from the same package and subclasses even if those subclasses are in different packages. This is mostly used for class members, not top level classes. Third one, default. When you don't specify any access modifier, Java applies package private access by default. This means the class or member is only accessible within the same package, not outside. Fourth one, private. This is the most restrictive. Private members are only accessible within the same class. You cannot access them from any other class even if it is in the same package. Understanding how those access levels work ensures proper encapsulation, modular design, and safe code exposure. Types of packages: built-in and user-defined. In Java, packages fall into two main categories: built-in packages and user-defined packages. Understanding both is crucial for working effectively in Java and structuring your own applications. Let's start with the built-in packages. Those are the packages that preloaded with the Java development kit. Java provides an extensive set of built-in packages that cover everything from basic language functions to advanced networking, file handling, GUI development, and more. Here are few important built-in packages. Java.language automatically imported in every Java programming. It includes fundamental classes like string, math, object, and system. Java.util contains utility classes such as ArrayList, HashMap, date, collections, and more. Java.io include classes for file input output operations such as file input stream and buffer reader. Java.net supports networking features like sockets and URLs. Java.sql provides classes for accessing and processing data stored in databases using JDBC. Now let's talk about user defined packages. Those are packages that you, a developer, create to organize your own code. This is especially useful in large scale projects where modularity and clarity to create a user defined package. First one, add a package statement at the top of your Java file. Second one, save the file in a folder with the same name. Third one, compile and use the class in other files by importing it using the import statement. Using user defined packages allows you to build your own custom library of reused components, making your code cleaner, more organized, and easier to maintain. Creating a package. Let's now go hands on and see how you can create your own package in Java. This is a fundamental skill when organizing code in real world Java applications, especially as projects become more complex and involve multiple classes. Creating a package is simple but follows a structured process. Let's go through it step by step. First, you define a package name using the package keyword at the very top of your Java source file. For example, package my package. This statement tells the compiler that the class defined in the file belongs to the myPackage package. Now let's talk about the file structure. Your Java file must store be in a directory structure that matches the package name. So in this example, your file should be placed inside a folder named PyPackage. This is important because the Java compiler and runtime use the folder structure to locate classes. To compile this file, navigate it to the directory above my package and use the javac command. Javac my package. This will generate a .class file in the same folder. To use this class from another class in a different package or directory, you need to import it using the import keyword, which we'll discuss in the next slide. Creating packages help you keep your code modular, maintainable and scalable. It's also a great way to promote reusability, especially if you are building libraries or frameworks. Using a package in Java. Now that we have created a package, that next step is learning how to use that package in another Java class. This is where that import statement comes into play. It allows you to bring in classes from other packages so you can use them freely. Let's take a look at a simple example. Suppose we have created a class called message inside a package named my package like this. Now let's say we want to use this message class from another class located outside the my package. Here what's happening? The import statement tells the Java compiler where to find the message class. Once it's imported, we can create objects and class methods just like we would with any other class. If you don't want to import individual classes, you can use a wildcard import to include all classes from a package. If the package contains many classes and it's generally not recommended for large scale applications, this mechanism of importing classes help you reuse components and maintain clean separation of concerns, which is a fundamental principle in software design. Access modifiers and packages. Understanding how access modifiers interact with the packages is crucial when structuring your Java applications. Java provides four main access levels: a public, protected, default or no modifier, and private. Those control the visibility and accessibility of classes, methods, and variables and are deeply tied to how packages work. Let's break them down one by one in the context of packages. First one, public. When a class, method or variable is marked as public, it is accessible from anywhere, even from outside its package. If you want a class to be used across your application or by third party users, make it public. Second one, protected. This modifier is more usable. It allows access from the same package and subclasses even if those subclasses are in different packages. This is mostly used for class members, not top level classes. Third one, default. When you don't specify any access modifier, Java applies package private access. Importing classes from packages. Now let's focus on the practical aspects of importing classes from packages. This is something you do in nearly every Java program, whether you are using built-in libraries or your own custom packages. In Java, the import statement allows you to bring external classes or entire packages into your current file. So you can use them without needing to type their fully qualified names. Let's start with a basic example. Import java.util.scanner. This imports just the scanner class from the java.util package. Now in your program you can simply write scanner input equals to new scanner. Without the import you have to write java.util.scanner input equals to new scanner. So importing makes your code cleaner and easier to read. You can import all classes from a package using an asterisk. Import java.io.asterisk. This statement imports every class from the java.io package such as file, buffer reader, import stream and more. However, it does not import subpackages. For example, if java.io has a subpackage java.io streams, you would still need to import that separately. While wildcard imports can be convenient, they are not recommended for production code, especially in large products because they make it unclear which classes are actually being used. Can lead to naming conflicts if two packages contain classes with the same name. Finally, remember that Java.language is important by default in every Java programming. So you don't need to explicitly import classes like string, math, or system. Static import in Java. In this slide, we will explore a useful yet often underutilized features in Java. Static import. Introduced in Java 5, static import allows you to access static members, that is, static methods and fields of a class without qualifying them with the class name. Let's take a classic example using the math class. This works perfectly, but it requires you to prefix every static method with math dot. If you are calling multiple static methods from the same class, this can clutter your code. With static import, you can write import static java.language.math.star. Now all static members of math like square, sqrt, power, pi, and others can be used directly without the class name. So when should you use static import for readability? When you are using many static members from the same class, static import can reduce redundancy and make your code cleaner. For constraints, static import is often used to import constraints from utility classes like java.language.math, java.time.day of week, or your own constraints class. Overusing static import can make your code confusing, especially if it's unclear which class a method or constant belongs to. If multiple static imports have the same method name, the compiler will throw an error. Subpackages are nested packages. As your Java applications grow, organizing your code into a flat structure of top level packages becomes impractical. This is where subpackages or nested packages come into play. They allow you to build a hierarchical structure of packages, just like directories and subdirectories on your computer. In Java, a package can contain other packages, those are called subpackages. The naming convention use dot notations to define the hierarchy. Com is the top level package, often based on the company domain. Example is a subpackage under com. Utils is a subpackage under com.example. This hierarchy is not just for names, it's reflected in your folder structure. If you create a class inside com.example.utils, it should be located in a folder path like com example utils your class.java. This structure provides several key benefits. Separation of concerns. You can group related classes by functionality like com.app.model, com.app.controller, and com.app.service. Improved maintainability. Larger teams can work on different subpackages independently without stepping on each other's toes. Clear naming and easier navigation. It's easy to locate where a class belongs just by looking at its package path. It's important to note that subpackages are not automatically imported when you import a parent package. For example, import com.example.star. This does not import classes from com.example.utils. You must import subpackages explicitly. Proper use of nested packages contributes to clean, scalable project architecture, especially in enterprise level applications. Packages naming conventions. When working with packages, following consistent naming conventions is essential for clarity, uniqueness, and maintainability, especially in large or collaborative projects. Java recommended conventions are straightforward but powerful. First one, all lowercase letters. Package name should use only lowercase letters to avoid conflicts across case sensitive file systems. For example, package.com.example.utils. Second one, reverse domain name. To ensure uniqueness, start with your organization's domain name in reverse. If your company domain is example.com, your packages begin with com.example. Third one, hierarchical structure. After the reverse domain, include additional components that reflect project, module, or layer names. For instance, com.example.project_name.service, com.example.project_name.model, com.example.project_name.controller. Fourth one, avoid using Java received words. Since package names become part of fully qualified class names, avoid keywords like in class or static in your package structure. Fifth one, be descriptive. Choose names that convey the purpose of the package without being overly. Sixth one, no special characters or underscores. Stick to letters and numbers only. Especially characters or underscores can cause confusion and are generally discouraged in package names. Seventh one, consistency across the code base. Once you have chosen a package structure and naming pattern, apply it uniformly across all projects in your organization. This consistency helps developers instantly recognize where to find classes and reduces onboarding time for new team members. It becomes easy for anyone, whether part of your team or external collaborators, to understand the structure, locate classes quickly, and avoid naming collisions. Interface and package integration. In this slide, we will explore how interfaces and packages work together in Java. This is an important concept because Java is designed with modularity and abstraction in mind. Interfaces allow us to define a contract or a blueprint that other classes can implement. On the other hand, packages help in organizing classes and interfaces into namespaces, providing structure and preventing name conflicts. Let's start with the interface part. In the code, you can see an interface called greeting. It has a single method declaration. White say hello. Notice that this method does not have a body. That's because interfaces in Java only define what needs to be done, not how. The implementing class takes care of the actual logic. Interfaces are very useful in scenarios where you want to enforce a certain method structure across multiple classes. Now look at the package greeting statement. This line declares that the class belongs to a package named greetings. This means that the class and interface can be stored in a folder named greetings, and any class that wants to use them must import this package using the import keyword. Finally, the hello class implements the greeting interface. It provides the actual definition of the say hello method, which simply prints out of message hello from package. This is how interfaces and packages work together. The interface defines the contract and classes within packages can implement that contract to provide functionality. This approach promotes clean coding, reusability, and better project structure, especially important in large scale software development. Best practices for interfaces. In this slide, we are going to focus on the best practices for using interfaces in Java. Interfaces are a powerful feature of the Java programming language, and when used properly, they contribute greatly to the flexibility, modularity, and maintainability of code. However, it's important to follow a set of best practices to ensure you are using interfaces effectively and avoiding common pitfalls. First, one of the fundamental best practices is to use interfaces to define types. Instead of coding to concrete classes, you should always program to an interface. This allows you to change the implementation later without altering the code that uses the interface. For example, if you create a method that accepts a list as a parameter, it should not care whether it's an array list or linked list, just that it's a list. This promotes code generalization and allows easy switching of implementation if needed. Second, always prefer interfaces for abstraction. Abstraction is a core concept in object oriented programming, and interfaces are one of the cleanest ways to achieve it. When multiple classes share a common behavior, defining that behavior in an interface allows all of them to implement it in their own way while still to a common contract. This makes your code base easier to extend and reduce duplication. Best practices for packages. In this slide, we will focus on the best practices for using packages in Java programming. Packages play a critical role in organizing and managing code efficiently, especially in large scale applications. Following packages Following package best practices ensures your code base remains clean, maintainable, and scalable over time. Firstly, always aim to keep related classes in the same package. Packages should act as a logical containers for classes that serve similar purposes. For example, if you are working on a student management system, you might have separate packages for students, courses, enrollments, and utilities. This not only improves organization but also enhances readability and makes it easier for team members to locate and understand components. Secondly, it's important to avoid large monolithic packages. When too many unrelated classes are bundled into a single package, it becomes overwhelming to manage. It increases coupling between classes and reduces modularity. By splitting code into smaller, focused packages, you promote the separation of concerns. This allows different teams to work on different parts of the application independently without interface, leading to faster development and easier dubbing. Finally, use clear and consistent name for your packages. Naming conventions in Java typically follow a reverse domain name structure, such as com.companyname.project.module. Names should be meaningful and reflect the responsibility of the classes within. Always use lowercase letters for package names to avoid conflicts with class names. Best practices ensures that your Java projects stay modular, understandable, and easy to maintain, which is essential for any professional grade software development effort. Common mistakes to avoid. In this slide, we are going to highlight some common mistakes that developers often make when working with interfaces and packages in Java. Avoiding those pitfalls will help you write clear, more maintainable, and professional grade code. First, one major mistake is implementing too many unrelated interfaces in a single class. While interfaces are designed to enable abstraction and multiple inheritance, adding too many unrelated interfaces can make your class bloated and confusing. The interface segregation principle, one of the solid principles, which states that a class should not be forced to implement interfaces it does not use. Instead, split the functionality into smaller, more focused interfaces and let each class implement only what it truly needed. Secondly, many developers unintentionally use default or package private access modifiers for classes and methods. In Java, if you don't specify an access modifier, the member gets package private access by default, which means it is only accessible within the same package. Use public for classes and methods that needs to be accessible outside the package and restrict access using private or protected when necessary. Third, ignoring naming conventions can lead to disorganized code that's hard to read and maintain. Java follows standard naming rules. Class name should be start with uppercase letters, method and variables names with lowercase, package name should be lowercase and hierarchical like com dot example utils. Proper naming not only improves readability but also helps team work more efficiently together. By being mindful of these mistakes, you can improve the quality of your Java code and make your projects easier to scale and debug. Conclusion and key takeaways. As we conclude your discussion on interfaces and packages in Java, let's summarize the key takeaways and highlight why mastering those two concepts is essentially for writing clean, efficient, and modular Java programs. Firstly, interfaces serves as the backbone of abstraction in Java. They allow developers to define method contracts without specifying their implementations. This is not only promotes flexibility and scalability but also supports one of the most powerful concepts in software development. By coding to interfaces rather than concrete classes, you allow your application to be more dynamic and easier to maintain or extend. When different components communicate through interfaces, changes to one component don't ripple through the entire system. Make your code adaptable. Secondly, packages play a crucial role in organizing code. They act like folders for your classes and interfaces, grouping related code together and separating unrelated concerns. This structure enhances readability and navigation, especially in large projects. Packages also help prevent naming conflicts, as two classes with the same name can exist in different packages without confusion. Proper packages use also supports encapsulation, allowing you to restrict access to internal classes and expose only what's necessary to other parts of the program. Finally, the combined mastery of interfaces and packages leads to modular and well structured Java applications. You will find that your code becomes easier to test, refactor, and debug. Thank you all on happy coding with Java. Wishing you all the best on your programming path.